And welcome to a slightly different episode of the Let's Learn Zig series. So, what do I mean by that? Well, we're not going to go in teaching a new feature, new thing in Zig, or just how the language works, but rather Zig 0.16 was just released recently. So, I want to dive into what's new. Oh, yeah. And one other thing I want to call out, if you want to actually see me upgrading something to Zig 0.16, I have a video. It's going to be one of the corners of upgrading my game engine series from Zig 0.15 to 16. And yeah, so if you want something maybe a little bit more hands-on, that's going to be there. I know this was a pretty big change, and there's a lot of cool stuff out there, especially the big one obviously being the IO. There's a lot to it, and that's where we're going to spend the most time today. So this will still look like a normal kind of Let's Learn Zig episode where we'll go over to the computer and show off some code. So I'll go through various examples of the new things and kind of everything that's in there. There's also a page of the release notes, so we're going to walk through that. Just to kind of preface, we're not going to go into every single thing in the release notes. There's a lot of stuff there, especially when it comes to the targets for the compiler. So we're not going to get into that. I'm more focusing on actual kind of features and language changes. And I think that's going to apply to most developers out there. So going to try and keep it focused on that. So I hope you guys enjoyed the video. And yeah, let's dive in. All right. So we're here in the release notes. So if you want to come see for yourself, it'll be ziglang.org/download/0.16.0/release notes or release-notes.html. And that'll bring you to this page where one, you can go download the latest version, and it is going to bring you to kind of what we're going to go over today. So I do want to just quickly say some stuff. We're not going to go over every single thing in this list. There's a lot of things in the update. I want to go over more of the bigger picture items and just help with that. And we're not going to get into things like target support. Like if you look, scroll down, there's this big section around targets that you can compile to and kind of where its support is at. We're not going to dive into that today. We're going to get into more code changes, language changes, syntax changes, things like that. So one of the things I first want to go to is this juicy main. So now this is something that's actually quite nice. So it's called juicy main, and what it means is we can now pass a parameter called process.init into main, and it gets us access to all of these things. So another option is you can pass minimal. I'll get to that. So one, if you need like a permanent storage for the lifetime of your application, it gives you an arena allocator. Or if you want a GPA, so this is going to be the same as like the testing or more debug tool for you. So you'll use this one if you want to kind of maybe in debug mode, you want to be able to ensure you're not having memory leaks. And then gives you a default IO based on whatever your configuration is. Then also pre-opens, not as relevant for today. And then here again, if you just want minimal, you'll get the environment variables and the command line argument variables. So there's an example here, but I also just want to kind of get into the code itself. So here is a very basic example of what that looks like. So we see here, we have main init. So I see process.init. That's the exact same thing we just looked at. This is now a valid kind of definition of main. So we see we have that arena allocator where we're actually allocating with minimal, or I guess with the arena. So the arena there, we're grabbing the args off of minimal. So if you remember, we can just kind of dive right into it. Minimal was like command line arguments and the environment variables. So we look at all the args and now we can kind of own them and then print them. And then this doesn't actually do anything, but I just show we also get an instance of IO, which we will dive more into IO very soon. But then you can kind of create a writer, and this is the actual writer you'll use. So if you look at std out writer dot, this actually gives you the write functions. So you can write to wherever you need. And another cool thing in this case, the file is std out. You can have an actual file that you open. So that's also going to be using the new IO interface, but let's just run this and see what happens. So as we can see, all your code base belongs to us, and then the arg is the location. So then if we actually want to see those variables, we can do this, and then let's say like 1, 2, A, B. Now we're printing all the variables passed in, which is exactly what this program does, but it just calls toSlice, which takes the arena allocator and actually turns into a slice for us to have. And then one last thing again, another valid definition is one, nothing, or you can have this be minimal. And we're not actually really gonna use it, but we see we have minimal just args due to slice, or really any of these. We can say iterator. And then while iter.next, cd debug print. Just a typo. And now we kind of just have the same thing. So if all that was a lot, we can see we can use minimal. And again, this is valid. And now we can just kind of iterate through our args and print them, which does the exact same thing, this time with no heap allocations. So coming back here, we can see there's a lot of language changes. Again, I don't want to go through every little thing here, but I do encourage you to check if you're doing anything like this. We can now see, for example, packed union can now be used like this. Obviously before you couldn't. See translate. This is a pretty cool one. So now you can almost have, instead of using C import and C includes, now you can just have your single like normal Zig input. But then at build time, you can use translate C to now turn that into like a header file into an actual library. And you can link it against whatever you need. And you can give it a name and import it like normal. Okay, so now we can kind of see what this C example looks like. So if I head over to my build, you can see I added this. So this is the new add translate C, and it's going to take the C demo.h, which has two things, one being a simple adder function and another being a string length function. So all like pretty standard stuff from C. So now we can see we came over, we created an import, we created a module from that translate C builder step, and then now we have an import. So if we go back and look, we can just import it like this, and it should just work. So we can see we have our import C, and we have those functions, cdemo add and cdemo str length. Now if we run that, see that's exactly what we want. So 40 and 2 is 42. Then the string length of this arg is 56. So that's pretty cool, because before we would have done something like this, C equals at C import, which would have been at C include, which then would have been wherever the path to this is, cdemo.h, and we've just been, see how, like how much simpler this becomes in your code. So all we're doing is now offloading more stuff to the build system to help clean up our actual code and make really just C code look even more like regular Zig code. So I think that's really cool. Okay, and this next section is the at type being replaced with more specific things. So instead, so you used to be able to do like at type, and then you'd pass in like things for int, or you're using something like sc.meta.int. So there's a lot of examples here, but I just wanted to show a couple small ones. So in this example, like you're saying, so you do add type, and then you'd say like .int, and then signedness. So all that pretty explicit. So now you can just do something as simple as add int, signedness, and bits. We can see that, and then you create your own kind of U10 type or an I24, or you can define a pair. This one could be very useful for you because it's all comp time, or something like a mutable pointer into a U8. So like before and after, things get a lot easier. Or now a really cool thing is something like using at struct to now create a vector type, for example. So now we'll get into the usage of this one, but you can see how we can do like make vec. It'll be an F32 and it'll be 3. So then that creates a struct just like this. So as V0 to 2, and they're all the types. So this unlocks some very powerful stuff, as you can see, or you can have a color enum. So now we can see it can only be red, green, blue. And then the zeros will obviously be 0, 1, 2, 3 because it's an enum. And then, yeah. So now we can actually, let's run this and then compare the two. So we can see the bit size of U10 is obviously 10, and U20 or I24 is 24. And now we have this pair, and you see it's a pair of things that are different types. Very cool. So if we look, we print it 42 and answer, or we do this kind of like, or we have the mutable pointer. So we see we have 10, and now we're saying a U8 mutable pointer. So it's going to be a reference. We add 1 to that. So it goes from 10 here to 11. Or we have that vec3. So obviously this is what we're just looking at with the v0 to v2, and then also color. So now these are all things that are just a little bit less code than used to be. If you had used the at type, it's all just a tiny bit simpler. That's very nice. Okay, and now getting into like probably the biggest thing, which is the new IO interfaces. So I've created just a very simple example of reading from a file and writing the std out. So if we go over to this hello.txt file, we see we have hi there. That's it. That's all we have. And now all we're going to need is what's on the screen right now. So as we already talked about, we now have init, which makes it very easy. So we see we can, wherever we need IO, which now are going to be things like open file, it's going to take, you can see an IO right there. And similar with a reader is going to need IO. And same thing with a writer. We already saw this at the start, but creating a writer to std out, we're going to need an IO. So now all these things are going to just need IO. Same with even closing the file. So for now, we're just going to use what's in here, but then also I'm going to add in how to create your own IO. We'll probably just use started. So let's walk through this. So one, we open the file. So we're opening hello.txt from our current working directory. And then we'll defer file.close. So that part should be normal, just taking in the new parameter. And now let's make a reader. So one, we're going to need a buffer for a reader. So I'll have that. And then we'll go over and actually create a buff reader. So this syntax is a little strange. You kind of got to get used to it, because I know when I read this, I would expect this reader to just, I'd be able to start using it as a reader. As you can see, the type is reader and this one's pointer reader. It's a little bit strange, but you don't actually get these functions until you grab a pointer to the interface or a reference to the interface. So this is the true reader we want. So this will return a generic reader type, but we actually want the interface attached to it. If that makes sense. Because this, as you can see, it comes from IO. So this will be kind of whatever IO we're defining, which we're getting it from init right now. But again, we'll define our own IO very soon. And then, so now we have a reader to the file, to the hello.txt file. So let's just read, in this case, the first 10 bytes. There's lots of different functions to actually read. You can take a look here. If we just do reader, read, you can see slice endian, short, vec, all. You can do stream, lots of different things in there. But just to keep it easy, and I also want to show again how you can use the allocator from init. So we'll just read that. And then I guess a better way to do it is init gpa 3 would be bytes, instead of doing that at the end. That's the more zig way. So then there we go again, just a usage of the init GPA, which also would catch a memory leak, which I'll show at the end. But if we comment this out, maybe we'll even just do it now. If without this, it'll show a memory leak. So I just want to show how GPA is that kind of debug allocator that we used to have in previous SIG versions. And then just like before, we saw this earlier. So we're creating a writer. So .init, and we're just going to be standard out. We could open up a new file and just write to that. It's very similar. So in that case, instead of passing std out, you do exactly what you did up here. So let's even just do this. Let's say file 2, and open file will be hello 2, or instead of open file, actually, it's going to be create file. So now we have file 1, file 2, which I'm not actually going to use this yet, but I just want to show, because I want to show the first example. So let's finish getting through it. So we create a writer, same thing with the interface, and then we just write the bytes that we read from up here. So let's run this. And there we go. We get hi there. And then, as I said, it's a memory leak. So let's rerun it. And there we go. So we're reading hi there, and then we're writing it out to standard out. But now, as I talked about earlier, if we get rid of that and now point it to file 2, so let's do an ls, we can see everything that's in here. So we actually did create it. So it's just one cat hello 2, just to show that we didn't actually write it last time. And let's remove hello 2. So now let's run it. And now if we cat hello2, we wrote it in there. So now it was that easy to replace standard out with just creating a new file and writing it into there. All you had to do is replace this one param. So I think that's very cool. Going from standard out to a file, it's very easy to interchange, and that's kind of the goal of this. So now let's do one extra thing and actually create our own kind of IO instead of using the one from init. Okay, and now we're back. So what I've done here is added these 3 lines. So all we're doing is now instead of using init.io, and I guess I changed it, so now we're using io instead of init.io everywhere else. So yeah, so we create our own io instance instead of using one given to us. And then there's options here if you want. You can see there's concurrency limit, async limit, stack size. So if you want to play around, you can do that. But if we just go ahead and run it, you can see it's the exact same thing. Sorry, coming back here. So obviously I just showed threaded. So that's based off threads, which we can see like IO operations, everything is basically threaded. So it's very cool. You know, it's nothing crazy. Again, it's based on threads. But if you want to use maybe something a little more experimental, this is evented, which is more supposed to be like kind of green threads, or if you use Golang, Go routines, things like that. So it's supposed to be lightweight threads that you can spin up lots of. So again, this is work in progress and experimental, but that's exactly what you want. And then I guess there's one more called IO failing, which is just simulates a system with no supporting operations. So not very useful for us, but yeah. So these are kind of what you can use right now. Threaded will be your main one for a while as Evented's getting worked on, but just wanted to share. The last thing I want to get into is actual usage of like futures and async operations, because that's a little bit more exciting than just reading a ring to a file. So this is gonna be the last kind of demo for today. And yeah, so let's get into that. Okay, now let's get into this code. So this is gonna be by far the most complex thing because we're gonna cover futures, groups, queues, select, batch, and then different time things. So for example, just let's run it and see what the output is, and then we'll kind of dive in. So we can see there's a few things here: squared, winner of a value of 4. So we can see that happens every time. Then we can also see the duration. So one kind of thing is that we're going to need for this is a kind of slower function. So one that is just going to sleep for say 10 milliseconds. We can make that longer, make it a little bit more noticeable too. We can see now we're waiting, and then took 2 seconds, but see it took a little bit longer. So that's kind of this slow task. So you could imagine it's something like going out and fetching like a network or an API call or something like that. So now we have a producer. So this is going to be taking one of the new queues and obviously IO, and it's going to put one onto a queue. So we're going to take one of these slow squares and put it onto the queue, and then take one, which is going to use that same kind of queue. But this one is just going to grab an item from the queue. So this will actually pull it off. And we can also see here one kind of key point is producers are what's slow because we're actually calling the function here. So producing is slow, but taking it will take whatever is returned from it. So we also just have a helper nap function. Okay, so now let's see, how do we get the start time? So it's going to be under the new IO clock timestamp, we dot now. This is the same, so we're reading in, and then we're going to have all the bytes. And now one cool thing is futures. So this is kind of like what you'll see in other languages with async await. We're going to use std.io.async, and we're going to pass the function and the args. So in this case, however many bytes we read, we're going to perform that slow square and return a promise essentially, or a future. If you're coming from JavaScript, it's a promise. Other languages called a future. So one, we can see we may need to cancel it. So if we reach the end, we can cancel it, or we await. So what does await mean? It basically is like async await. So if this was JavaScript land, this would look like const squared equals await slow square, and then it was bytes.length. So let's just do bytes.length. So if this was JavaScript, this is exactly what this code would look like. You're just awaiting slow square, and then the argument was bytes.length. So I hope that kind of helps clarify things if you're coming from that world or other worlds. It's the same thing, but just in Zig's way, and everywhere along the way you're passing in an IO. So now going back to the queue, we can see we can create a queue from a buffer. So this queue is only going to hold 8 values. And then this is where the producers and consumers are going to kind of take from that queue. So we can see producers, it's taking that queue. So what we're going to do is we create a group. So, and then add 3 producers onto the group, and then we wait it. So what's going to happen is we're going to wait all these at the same time. And in JavaScript world, if we're going to keep that up, we don't even need that. It's going to be something like promise.all. And then let's see. So it's going to be produce 2, produce 3, produce 4. And that's what this kind of looks like. So this is how you do like a group all at the same time, because you just have a single await. So that's kind of what this looks like. So now getting into one last thing is the select. So this is kind of the last bigger thing that we're getting into from IO. So let's see. It runs tasks whose results differ in type, return the first one. So you can see, so a winner, so we're going to have 2 items here, and we're going to create that select from the buffer of 2 winners. And again, it's going to be the take IO. So now we're going to call async on that. So we're going to have 2 different functions. One's take 1 and one's nap. In this case, napping for 500 milliseconds versus take 1. So if you remember, take 1 should be very fast. So this one should always win the race. But then this is essentially kind of like a timeout check. So you might be confused, like, why would we want this? Well, let's say take 1, we don't know how long it's going to take, but we know we want it to take less than 500 milliseconds. So whichever one finishes first is our winner. So I hope that makes sense. So this is essentially a way to cancel or have timeouts. So if this is, again, an API call, you're like, I don't want my API calls taking more than 500 milliseconds, or it's a DB call or anything, you can set something like this up, being like, ideally, the API call is done, but if it takes longer than 500 seconds, then we can cancel, or we essentially just cancel the API call. And then you can check on the winner. So maybe if winner equals value, that means we know the API call succeeded. But if it equals timed out, then we're like, okay, we timed out. Let's maybe retry or handle this gracefully. So one thing I did want to show is just to show you that it is a true timeout, is if we go back to our winner, we see this is from 500 milliseconds versus take 1. What I just did inside of take 1 is add, let's even just make this 600 milliseconds. So now there's a likelihood it's going to time out because it's taking longer than 500 milliseconds. So now if we run it, just wait a second, and now we see we timed out because it took longer than 500 milliseconds. If we do 490, once it runs, we should see it. See, it's back to the value of 4. But then as soon as you get over that kind of 500 millisecond range, it's timing out, and now you can work with it. So now we went through groups, winners. There's one last thing I want to kind of show off, and that's the combination of storage and batching. So in order to, it's going to be very similar to groups. So grouping is a way to group together async tasks and await them. And batching is quite similar, but there's just a little bit more powerful things we can do. So let's kind of combine things in a way. So we'll have storage for a batch. So in this case, we're gonna have 2. So that's already one difference. In group, there is no kind of storage. It's just you add them. So this, you know explicitly how many you're gonna have. And in this case, it's gonna be, we're just streaming to a file. So let's create a batch and defer canceling it. And now, remember how we did this to kind of have a timeout emulation? Well, you can actually just use sc.io.timeout, then the duration, which in this case is 1 second. So now we can await concurrent. So that's the benefit of the batch, is all this is happening at the same time. And we can pass that timeout to make sure it doesn't happen or take too long, any of the things. And at the end, we see how long things take. So we take this all together, we see, remember where we were. So 1 is going to be elapsed. So how long did everything take? Our winner and squared. So let's go back and look, where did squared come from? Squared was the result of just waiting for a slow square of byte.length. So squared equals 100. So that means we're squaring. So that means it was 10 bytes. So essentially it was saying that if we look, hello.txt is 10 bytes. That's what that says because it was square it, so 100. So the winner was the value of 4. So what does that mean? So if we look here, we have the queue, so we have take one from the queue. So the winner was 4. So if we go back up here, we can see we produced 4 different things in order. So 4 was the last one. So 4 will be taken every time. So again, if we run it a few times, 4 and 4 again. So again, it works just like a queue. This gets put on and it'll be the first one taken off. So that's why 4 is there and it doesn't time out. So that's all the code for today. I hope you guys found value. Again, there is still a lot of things in here. So I highly recommend you go through this, look at it. There's a great table of contents if you just want to look at language changes, or here again is all that IO stuff. So again, we just went through features groups, cancellations, batching, sync, time, we went through files, not as much networking, process, and entropy, but there's just so much. I don't want to take up too long of a video, but I feel like I tried to show what I found was the most important things, and I hope you find value. And yeah, thanks. And I hope you enjoyed it. I think it's cool that Zig's continuing to push new features, new things, changing the language. I know that can be pretty annoying for a lot of people, having to upgrade the compiler and then have tons of things break. But personally, I'm okay with that. I think it's fun. I think it's cool to see new things. And also, I think it's almost a good way to learn or check out the changes. Because if you're used to a compiler like Go, which never has any breaking changes, which again has its own benefits, but you may not be as in tune with what's changing in the language and new things. But if you're forced to upgrade and change your code, you're probably going to spend more time at the release nodes, seeing what's new, seeing what's out there. And I think that can be a win. It may not be a win for everyone if you're in production systems. Probably not a win, but as like working on something as a hobby, it's great. But yeah, I mean, I hope you guys enjoyed the video. I hope you learned something. I hope this will make upgrading a little less scary when you go do it in whatever project you have. And yeah, if you have any feedback, please leave it down in the comments, or there's a Discord link down in the description. Come say hi. It's always great chatting with you guys. But yeah, that's all I have. So have a great day.